Hi guys, it's Ivo here, and in today's video we're going to talk about database indexes. Since it's more of a theoretical topic, I've prepared a presentation which we're going to use. Initially, I wanted to make a single video covering everything about database indexes, but unfortunately it's a huge topic, so I'm going to split it in parts. In the first part, the current one, we're going to cover the following sections. First, why indexing is a developer's task. Because usually to analyze the database and understand how the application uses it, you will need to have a bit more application knowledge. So it's impossible for database administrators or external consultants to um, determine which are the best indexing scenarios. So it's a good idea to have that knowledge as a developer and choose the best indexing, because you will have a lot of information from the application code itself. After that, we're going to cover the anatomy of a non-clustered index, what an actual index is all about, what it has behind the scenes when you create an index, what happens in the database. And we're going to cover the two important data structures used from any SQL database actually to create indexes, and that's B-trees and doubly linked lists. We're going to cover when indexes become slow and what kind of different parts of the index can have a performance issue with your queries. Afterwards, we are going to look at what are execution plans and what to look for when we try to index our database. Finally, we're going to start looking at more details, and we're going to cover the where clause in this video. In my next video, which will be published in August 2020, I'm going to cover the various other operations in the SQL language, for example, grouping, sorting, joining, and more. I'm going to cover different myths that exist among developers, and I believe these two videos will be more than enough for database indexing knowledge. So let's start. First things first, a developer should understand how indexes work. They should understand when to apply indexes, and they should understand what is happening in every query in the database, because normally developers kind of tend to use either an object relational mapper, for example entity framework in the .NET world, or they tend to rely on external database admins for proper database optimization. But actually, from indexing point of view, that's not the case, because usually how the data is queried is in the application code. External database admins or external consultants cannot see that all that knowledge. They have to seek in the code, and while they have to do that, you already have the knowledge in the code, and you already can determine whether an index operation is good enough for you or whether it's bad. Um, so the development team has all that information right away, and the development team can decide whether the current state of the application needs indexing. Because as your application evolves, your indexing situation may evolve too. Initially, you may not need an index in your database, but after your queries become more complex, you may decide that an index is uh, mandatory, and that's developer's task. So As a developer, we need to understand how indexing works, what is behind the indexing operations in the database, in a SQL database, and what's the difference between a clustered or non-clustered index. So the difference between a clustered and non-clustered index. The clustered index is how the database is storing your data in the actual physical order. By default, a clustered index in SQL Server is the primary key, but you can customize that. Every time you create a primary key, essentially you create a clustered index. This is the initial order of the table. And you may know that when you create a table with the primary key, for example, an integer, the database is stored in the order of the primary key, in this example, the integer. And a clustered index is one per table. You cannot have multiple clustered indexes because the definition says it all. The clustered index defines the physical order of the data on the hard drive. Then you have non-clustered indexes, and these indexes are actually additional indexes created by the developer or created by the database admin, which may be more than one per table. It doesn't matter how many indexes you have, but consider this: each index adds an overhead and adds an optimization. So we're going to cover that, how what's the middle ground of indexes. That's the important part, because if you have too many indexes, your insert, update and delete statements will have a performance hit. But if you design your database so that only the most difficult and complex queries have an index, you should be absolutely fine. So the non-clustered index is an additional index which allows better searching. If you're not quite familiar with indexes in general, this is a rule you can follow. If you create an index on a column, you essentially make the searching for that column better. The searching will be more optimized. So every time you need this column in a where clause, for example, you have better performance. But there are some catches here and there, so I'm going to cover them. So an index adds a better search and better read, and you will find data faster. That's why we use indexes. But the negative side of an index is that every time you insert, update or delete data, that index needs to be rebalanced, needs to be restructured, and that takes time. So if you have a typical web application, indexing should be fine, because how many times do you go to, for example, Stack Overflow to search for data, and how many times you actually write on Stack Overflow or comment? Usually you search for data. So if your application has the following business requirements: users more often search data than insert, update or delete, then it's completely fine to use indexes. Otherwise, you may consider different options. For example, separating the table, for example, using different kinds of databases. There are databases which are faster for inserts and deletes, for example, but are slower for updates. So it depends on the business case. But when we're talking about indexes, they make searching a lot more faster. You will see how in a minute. And they make insert, update and delete a little bit slower. Usually the insert, update and delete parts are not that important, so the performance hit is not that huge, so it's completely fine to add indexes. But there are situations in which you add index without the need of it, or you add indexes and you don't understand how exactly indexes works. So this is the important topic, to understand how these indexes are created, what the database does for you when you create an index, and how to use it most efficiently. Also, how to analyze why an index is actually slow even though you added it. Good. So clustered and non-clustered indexes, usually developers are responsible for the non-clustered ones. You can customize the clustered index too, but that's in more advanced scenarios. So for example, a typical web application, you don't need to customize the primary key, the clustered index. It's sufficient enough with its default settings. Good, so let's start with the anatomy of an index. When you create an index, you create a distinct structure in the database. So if your table data is here, for example, you have a table with some data, with some columns. When you create a separate index, you create another structure which stores the data in a different format, in a different way. It stores the data so that it's easily and it's faster for a search. And this separate structure actually refers to the original table. So every time you search for an entry, and the database can use the index you created, it will search in the index first because it's faster this way, and then it will find which table rows refer to this index data, and then it will fetch the data rows for you. So typically the index is created for a better search, which when the search is completed, the database will refer to the original table. So every time you create an index for a column, for example, you have 3 columns. If you decide to create an index for the first column and then decide to create an index to the second column, you create different structures. So this index will be for the second column and this index will be for the third column. And if you have many indexes in your table, each insert, update or delete operation will need to rebalance and restructure these separate structures. This is why it becomes slower for these operations. But the important part is you store a separate data structure which is not included in the normal table. It requires a separate disk space. Consider it like a book index. Usually when you have a book which is a non-fictional book, for example a soft skills book, or for example a textbook for biology or any topic for that matter, usually you have an index of every topic covered in the book at the end of the book for the last 3 to 4 pages. And this index in the book is sorted alphabetically. So if you, for example, search for molecular structure in a chemistry textbook, you will open the index at the end and search alphabetically. You will search very fast because the entries are ordered in an alphabetical order. So you will find molecular structure, you will see that it's on page 52, for example, and you will open that page to read for molecular structures. It's the same thing here. You have a separate structure which points to the your original table. And when you search an index, you are searching like a printed phone book. If you have a phone directory containing all phone numbers in a city, usually the names of the owners of these phone numbers are sorted alphabetically. So it will be very easy for you to find John Smith, for example. You will go to S and find Smith and then look for John in the second column. So searching in an ordered data structure is very fast and very efficient. The only problem here is that the database changes frequently because a phone book, a printed phone book, it does not change that often. And if you want to, if you have a printed phone book that changes super often, you have a problem because you need to print the same phone book every day, for example. With the database, it's the same. The database changes frequently, so if you have a lot of indexing, you have an overhead of printing the book. So you will have a performance hit. This is why indexing should be a very considered operation. You should discuss it with your colleagues and you should design the database so that it's in the middle ground. The first structure the database uses is a doubly linked list, because if we store the data in a normal sorted list, for example with 1, 2, 3, 4, 4, 5, 5, 6, 6, 6, 7, 8, 9. A normal sorted list like that will have difficulties when you decide to insert data. Because this sorted list, notice that we allow duplicates, because usually when you create an index on a column, this column may have indexes. It's rarely unique, so we should cover duplicates. And if we have a sorted list like that, and if we use a normal sorted list, every time we need to insert a new value, for example, we need to add the value 7 in the sorted list, we will have a problem because the value 7 needs to be inserted here. And when we insert the 7, we need to reorder all the entries after this insertion. And if we have millions of records, that will be a very slow operation. For example, if I insert the number 3 in this example, I will have to move like 12 entries for this insertion, and 12 movements on the hard drive or on the memory are very expensive operations. Imagine what will happen if you have a million entries in the database. You need to move, for example, 500,000 entries from on the physical hard drive. That's very expensive and it's not efficient. This is why the data structure the indexes use is a doubly linked list. It's essentially a list which is stored in the following way. Now, the doubly linked list has nodes. These nodes actually contain the data, but the nodes are referring to each other by pointers. So each node knows which one is the previous node and which one is the next node. This is different from the normal sorted list when each node or each value knows its index. For example, this is on index 3 if we start from 0, like we usually start. So moving elements in a normal sorted list requires you to move a lot of data because you need to reindex everything. And if we change that structure to a linked list where each node only knows the previous one and the next one, and it doesn't know what order it has, what index it has, it's very easy to insert a new node. When you insert a new value, for example, let's say that this node stores 1 and 2, this node stores 2 and 3 and 4, this node stores 5, this node stores 6, 7 and 8, and this node stores 10. So when we need to insert a new node, for example, if we want to add the number 8 here, we just need to introduce a new node with the number 8 in it. We need to break these pointers, and we need to create two new ones. So inserting a new entry is a very efficient operation. You just need to change a few pointers and you don't need to move the entire list. So in the database, each database node contains multiple entries, and they are sorted, of course, and data is sorted in the nodes themselves and between them, like the example I showed. So here is an example of a database linked list. We can see that we have an index on this column, which is column 2, and initially the table is not sorted because when you the initial order and the sort of the table is defined by the primary key and the clustered index of that table. But when we create a new non-clustered index on column 2, for example, we sort that column, and the database creates a linked list with different nodes. For example, we have 3 nodes here which are interconnected. Each node knows the previous and the next one, and the data is sorted both in the nodes and both between the nodes. We can see that we have 11, 13, 18 in the first node, which is sorted, and then we have 21, 27, 27 in the second node, which is again sorted. Both these nodes are also sorted. After the linked list, there should be an efficient way to search for values, because we have a sorted linked list here, but what happens if we have tens of millions of records? It will be very difficult, although the entries are sorted already, it will be very difficult to search in the sort, because if we sort, if we have a sorted collection and we decide to search in it, it will be to search with a complex criteria. For example, we need all the values between 1 and 10, for example. It will be of course, it will be more efficient to search in a sorted collection than an unsorted one, but still we need something better, because if we want to search, for example, entry with value 100,000, which is quite at the end of the sorted index, we will still need to search every entry. We will need to see, is 11 100,000? No. Is 13 100,000? No. And so on. We will need to search the whole index from start to finish until we find the 100,000 value. And that's not very efficient. So we need another data structure to search values efficiently in the linked list. And that structure is the B tree. The B tree is the so-called balanced search tree. It's not a binary tree. Binary tree is a different beast. This is a balanced search tree. And the B tree has nodes too. We're going to see one in a minute. It has nodes, but what's important for it is that the B tree nodes refer to the biggest values in each linked list node. So each node in the B tree refers to the biggest value in the node in the linked list. If you are not familiar with data structures, I know this may sound confusing, but we are going to see a graphical example in a minute, so bear with me. So the B tree makes search operations in that sorted linked list super efficient. As a matter of fact, a B tree is never the bottleneck of an index. And when you create the index, the B tree behind that index is maintained by the database automatically. So every time you insert a new entry, delete an entry, update an entry, the B tree is automatically rebalanced, so the search is still efficient. And the B trees work super fast even with huge data sets. Usually the B tree is not the performance bottleneck of an index. There's a B tree simulator in which you may see how, I'm not going to show it, I just linked it here, but you may try to add different values and see how the B tree is created. You may check it out after you watch the video. So here's an example of a balanced search tree, or the so-called B tree. In the first node, we have these values, 9 and 30. The important part here is that all values which are below or equal to 9 are in this node. All values which are between 9 and 30 are in this node, and all values which are above 30, greater than 30, are in the final node. Then the same process is repeated for the child nodes. We have 3 and 6 here. So all values which are below 3 are here. All values which are between 3 and 6 are in the middle node, and all values which are greater than 6 are in the third node. And this is true for all the nodes in the B tree. So it's very fast to find a number. For example, we want to find the number 22. So we go to the root node and see whether 22 is less than 9 or greater than 30 or between these two. So we see that 22 is between 9 and 30. So we search for 22 here in this node. And we don't need to search in these parts of the tree. We no longer need to consider them. Then, when we see the number 22, we compare it to 12, 15, 19, and 26. And we can see that 22 is between 19 and 26, so 22 should be here in this node. And when we go to this node, we see that 22 is here. And this particular entry could lead to the actual table data. It may refer to the primary key. So if we're searching, for example, all the people who have age 22, and we have like 41 or more entries in the B tree, we don't need to scan through all the 41 entries. We need only 3 operations here, here, and here to find the person with age 22 and fetch its data from the original table. So a balanced search tree is very efficient in searching data. And you can see we no longer need to analyze the whole structure. On each step we just remove huge parts of the structure so that we can narrow our search. Okay, let's show another example. Let's say that we're looking for the number 35. Again, we compare in the root node. We see that 35 is greater than 30, so we go to the right. We compare 35 to 33 and 36. We see that 35 is between them, so we go to the middle node, to this one. And here we compare 35 to both nodes and see that the node is here. Again, with 3 operations, we found the 35 number. It's very fast and very efficient. Here is an actual example in the database. So if we have a linked list with sorted values, we will have a binary tree, not binary tree, a balanced search tree, a B tree, pointing to the leaf nodes of the linked list. So when and each entry in the B tree saves the biggest value in each node. For example, 46 is here, 53 is here, 57 is here, 83 is here. So what happens when we search for 57? We ask the B tree where is 57. Apparently it's not here because it's 57 is greater than 46. It's not here, and apparently it's here. So what the B tree shows us that we need to find the number 57 in the third node in the linked list. So now we no longer need to consider this and this node because we know that these nodes contain numbers below 57. Then what happens is that the database will open this node and it will compare the number 57, and it will see that we have 1 and 2 entries with the number 57. Because the last entry is 57, the database will need to check the next node too to see whether the first value is 57 too. So essentially we need to check 1, 2, 3 entries in the B tree and then 4 entries in the linked list to extract the two 57 values. Again, the database first searches the B tree by comparing the values, sees the actual value in which node, in which linked list node is, and then start searching for the value there. If the database needs to check the next or the previous nodes, it will check it, because when we have duplicates, the chances that we have 57 multiple times are very high. So the database needs to be sure and check the next node or the previous node in the linked list. So this is the important part how indexing works. So let's say we need to find all values which are greater than 55. So what the database will do is it will compare 55 to 46 and it will dismiss this node. Then it will compare 55 to 53 and it will dismiss this node too. Then it will compare 55 and it will see that the biggest value in this node is 57. So apparently we have values greater than 55 in this node. So database will start looking here. It will go to the node and it will see, okay, this the first value is 55, which is not greater than 55, so it will dismiss it. But all the next values will be, it will see that the 57 is greater than 55 and it will get all the values from the linked list. If there are more nodes below this one, it will search, it will get their values too. After the database gets all these entries, it will then get all the pointers to the original table, and it will know that, for example, the this row is this entry, this row is this entry, and so on. But searching will be super fast because of the B tree, the balanced search tree, and the linked list. This is super optimized in terms of finding data. Here is another example. If we search for the number 57 and we have multiple depths in the B tree, like here, we will need to find the number 57. Is it here? No. Is it here? Well, apparently 57 is below 83, so it will search in this node. It will dismiss all other nodes in the B tree. Then it will see, is it 46? Is it 53? We're searching for 57. Is it 57? Oh, here it is. So I'm going to look in this node. And apparently, because 57 is the biggest value here, it will need to check the next node in the linked list too, because the first value may be 57 too. So, considering all that knowledge about indexing and how indexing works and what data structures are behind the indexes, what may produce a slow index? First, let's consider the B tree. The B tree is super fast because it has logarithmic complexity. For millions of records, you may have 5 to 6 levels of child nodes. So if you have millions of records, you may have additional level and one additional level, and let's say another additional level. So in a B tree with million records, you will need only 6 operations to find a number. 6 operations in 1 million data entries is actually super fast. So the B tree is not a performance bottleneck. So the first ingredient for a slow index lookup is the linked list leaf node chain. Entries can be repeated, so the database needs to follow the linked list, the way I showed you in the previous example. And the second ingredient is accessing the actual table, because you may find super fast that 57 is contained 200 times in the linked list. So you extract all the entries from there, but you need to find these 200 entries in the original table. This is why it depends on the index, but it's a good idea to include additional data in the index. You may include it. We are going to cover that additional data in the next video, in the next part. But index lookup has the following step. Tree traversal, fast and exponential, usually not a problem. Then following the linked list node change. This may be slow for multiple entries. And then fetching table data. Again, it may be slow for multiple entries. So here's a myth on indexing, which if you rebuild indexes, that's a myth. If you rebuild indexes regularly, your indexes will behave better and will be more performant. That's not true, because rebuilding the indexes means rebuilding the tree, which is essentially fast. So we are not making anything in terms of following the linked lists and fetching table data. These are the most common ingredients for slow index lookup. So there is no need to rebuild indexes in terms of performance. To understand how our indexes work in different queries, we need to be familiar with the execution plan of the database. And in SQL Server, you can include the execution plan of your query by turning on Include Actual Execution Plan or just hitting Ctrl+M. The whole idea is that when you execute a query, you can see what happens with the query and how the SQL Server engine executes and finds the data in the query. So what are common operations in the plan which consider indexes? There are more, we are going to cover them in the next video, but for now we need to understand these 5 different operations. First, index seek or clustered index seek is a bit tree traversal which is performed efficiently. So when we see index seek, we know that we're performing at our best, so to speak. Then is an index scan or clustered index scan, which reads the entire index, all rows in the index order. So considering the seek and the scan, because they are very similar in terms of words, the seek is efficient because it does the same thing we saw here. It searches in the index directly and eliminates potential nodes which would not have the data we are searching for. But index scan means that the database needs to read every entry in the linked list, which is of course slower than searching through the B-tree. So index scan, if you see an index scan and expect the index to be performing efficiently, you may need to tweak your query or you may not create the right index. So an index scan shows you that there's a more efficient way eventually to use the index. There's a key lookup, which retrieves a single row from the clustered index, and RID lookup, which retrieves a single row from the actual table. So the key lookup searches in the clustered index, which is the primary key usually, we talked about that, and the RID lookup retrieves a single row from the table. Table scan reads the entire table, all rows and all columns. You may know already that table scan is the least desirable operation. In terms of performance, best to worst, I have ordered them here. First, it's the index seek. If you see index seek, you're using the maximum potential of the index. There's a clustered index seek, which finds the data in the primary key. There's an index scan afterwards, which is slower than the seek. We already covered that here. There is a clustered index scan, and last is table scan. So we're aiming for index seek if we can. There are situations in which we need to traverse the whole index, and that's completely fine. But if we can improve it, we need to search for index seek. So let's go to a SQL Server instance. I have a small database called Playground and table cats with 200 rows. It's not too much, 239. But that doesn't matter. What matters here is that we can include the actual execution plan in the query because by default it does not include it. We show the results and some messages, how many rows were fetched, for example. Good. To include the actual execution plan, we need to turn on this operation here, include actual execution plan, or hit Ctrl+M like Minnesota. So if we turn on the actual execution plan and hit F5, we will see a new tab here, which is called execution plan. So we will see what part of the query was the most inefficient. We will see what kind of operations the query needed to be executed. For example, the following query needs to execute a select statement from the database. It needs to execute the top statement, which is get me the top 1000 entries, and it needs to scan, notice, scan the clustered index. So what it did essentially is this query searched the primary key one by one, searched all of them because it's a scan, to fetch the data. And we can see what percentage of the query each operation used. The scanning was 99% and the top operation was 1%. So apparently the slowest operation here is the clustered index scan, but we're searching for all the data here because we are searching for 1000 entries and we have only 200, so it scans the whole index and we can see how many entries were scanned. If we put top 100 like this and go to the execution plan, we will see that it scanned 100 entries from the index. This is essentially, if it says clustered index, it's essentially searching on the primary key. I'm going to remove the top from here and I'm going to execute the query again. So now we can see that the top operation is no longer present and the clustered index scan was 100% of my query. If I try to find a cat by age, for example, I will see that the execution plan is again a clustered index scan, because what it needed to do, what the database needed to do here was searching through all the data in the index, all the data by the primary key, and search for that particular age. Again, if we run an equals operator, again it will need to search everything by the primary key and compare the age column. So what we can do here, if we have the following operation and our application regularly searches by age, then we can add an index. Adding an index is very simple. We can see that we have the primary key, our clustered index. We can just set new index. We want to add non-clustered index and hit add. Then I'm going to choose that I need to have an index on the age column. And afterwards, I'm going to name the index. I'm going to follow SQL Server conventions. Index cat's age. There's something wrong. There's an index. Let me see that. Yeah, there's an index. I'm going to delete it. And I'm going to add the new index on the age property. Like this. And I'm going to name it index cat's age. Like this. If we hit refresh, we will see that there's the cat's age here. So if I try to run again the following operation, I will see that it's again a search on the clustered index. So again, the index which was searched was the primary key. But why is that? I added an index on the cat's age. So I have an index on the age column. So why the SQL Server engine still searches by age in the primary key column? That doesn't make sense. It makes sense if we consider that we are fetching all the data here, because because the SQL Server engine is smart enough to decide whether to choose and search in the index of the column or search by primary key. And it determined that if you want to include everything, if you want to include everything from the database, it knows that a clustered index scan will be faster for this table because we have like 200 entries. So SQL Server again used the clustered index scan, which is a bit tricky. But what will happen if I decide to search only for the ID and the age? And let's try that. And we will see that now SQL Server decided to make an index seek, which is the most efficient operation, on the newly created cat's age index. So it depends on what kind of columns you are fetching to. So if you are wondering why your database is not using the index or why it's slow, you are going to need to execute the query against the execution plan, and you will see that if I add name here, SQL Server uses the primary key instead of the index I added. So if my queries are essentially fetch everything from the table, this index may not be needed. And if I want to improve the search, I will say, okay, let's remove the query and let's fetch only the ID and the age. Then the search will be optimized because it will use seek. So you need to see the query, execute it, and analyze the execution plan. If you see index seek, you're optimized enough. If you see index scan, then maybe something is wrong in your query or the index is not good enough for that query. But what to do if you need the name property too? So if I want to have the name property, I can see that I'm not using the index properly. I'm using an index scan on the primary key, which is not that efficient. What we can do is we can go to the index and say that we want to have included columns in the index itself. What that means is that we're going to have fast search on age, but we're going to have the data stored in the index for the name property, which will need to recreate the index. But from now on, if I try to query with the name and I filter on age, I will see that the execution plan now uses index seek on the cat's age. So apparently I improved the index by adding a column in it, and this column depends on the application code and what kind of queries I'm creating and I'm using. So that's important. It depends on the business logic, but the following index is now used correctly, and I'm using, and this query is as efficient as it can be. If we say that we need age greater than 5, we can see that again it's index seek, which is the performance optimization. Now, what are the common pitfalls with, so I already showed you how to use the execution plan for your queries. And now let's start with the tiny details, the common pitfalls. In this video, I'm going to cover the where clause, and in August's exclusive video, I'm going to cover other operations as well. So the where clause. The first thing is, let's say that I want to search by name too. I want to say that I want to search for for all the cats named Johnny in my database, I can see that it's an index scan. The SQL Server decided to use the index on the age to scan and find the name, but it's a scan, it's not a seek. So we can optimize that by adding another index, non-clustered index, which has the name. So I'm adding an index on the name. And then if I execute that, I will see that, no, let's fix it. We need the included column age here in that index because our query includes the age. And let's create it. I'm going to rename it to have a better name. Good. So searching on that, I will see that I have an index seek, what I'm searching for, in the cat's name index. So apparently that query is as optimized as it can be. But there are many pitfalls here, because if we decide to use a function in the where clause, usually developers think that when they create an index in the database on a column, they can use the column for whatever functions and whatever operations they want, but that's not true. If you decide to create a case insensitive search, for example upper, you will see that the index is no longer relevant. Upper name equals Johnny. Searching on that, we will see that we have an index scan. It's no longer a seek. It's not like it was without the upper. So apparently adding a function to your query will not use the index as optimized as you want it to be. So from a database perspective, the uppercase column is a different value. So it doesn't use the index at all. It doesn't use the index seek. It scans through it, but scan is slower. And we may expect that actually that's faster, but that's not true. So all user-defined functions or all functions which change the value essentially will not use the index correctly. So what we need to do is we need to create a pre-computed column. So we need to create a new column in the database. If we want this operation to be fast, we need to create a new name property, for example, upper name, a new column, pre-computed, and create an index for it. So if we want to use the case-insensitive search for this last name upper, we need to create another column, which is upper last name, with pre-computed values on the last name column, and create an index for that. But be careful. Do not over-index. Do not create an index for every single pre-computed value you may have, because you may create too many indexes. So what to do here? If we see that you have an index scan for a query, but the query is fast enough and your application doesn't have a bottleneck, don't do anything. This is fast enough. I'm happy with it. Even though it's an index scan, I don't care. It's fast enough. If I have a bottleneck on this column because I use case-insensitive search all the time and it's causing my application to be super slow, then I'm going to create the index. You don't need. All performance optimizations should be done after considerable amount of testing and considerable amount of measuring the actual performance. Don't optimize prematurely. You don't need to do it. You don't need to create indexes just to be safe in the future. Create indexes whenever you find your application having performance bottlenecks. The second clause is where clause with ranges. When you have a range search, for example, age between 1 and 4, let's go and try that. Age between 1 and 4. If we execute it, we will see that we have index seek. That's super fast. So the index seeking of the database is good enough for this query. But what happens when we have name equals Johnny and age between 1 and 4? If we go to the execution plan, we will see that it's still index seek. But how it works? So this is good enough and fast enough, and it's an index seek, but there's a catch. The catch is you can create an index on both columns, but which is the correct order? Because if we see that here we have an index scan, we can create a new index having both age and name. But what should be the order of the index? Because you may say first search by age and then search by name. This is like a phone book with last name and then first name. The index will be ordered first by age, and every time an age is the same, it will be ordered by name. So what's the correct order when you have multiple column indexes? The correct order is it depends on the query. So if we decide to create a multi-column index to cover the following scenario, what's the correct order? Because we already have index seek, but there may be a better way to do it. And the correct answer is index for equality first. So my index should be first on name and then for ranges. So I can improve this query by adding an index which includes first the name, because I know that the query searches for equality, and then the age. The name should be first because I'm going to search age for ranges. And why that is important? Because let's see the following example. Let's say that we need to search by date range in an index and then by equality by some ID. So what will happen if we search for date ranges first? The B-tree will find the range, the minimum range, and it will start traversing the linked list nodes to find the range of the query. So for example, if we search for January 1st until January 9th, it will need to search all of these values here. It will have a good range of 10 values or more, and then it will search among these ranges, among this range, it will search for the equality value. This is what happens when we have the range first and then the equality. It's still an index seek, so the execution plan will show it. If we go here, we will see that it's an index seek, so it's completely fine. But when we put the range first, we make a lot more scans in the linked list and then filter the data by the equality. What happens if we switch the order? If we switch the order and we first have the equality, we will have a smaller index range to scan, because the range will be a lot smaller when we first consider the equality. So that's important to optimize the queries. When you have such query with equality and a range, and if you are not happy with the performance of your query, create an index and put the first column to be on the equality and the second column to be on the range. That will save you a lot of index searches, like the example here. The same example with switched indexes. Then, work close with like operator. Avoid like expressions with leading wildcards. Example like this. When you try to search with leading wildcards, you do index scan, because the index needs to consider every entry for this wildcard. So the whole index is scanned from start to finish. And if you have millions of entries, this like expression will perform a scan. But you can search with ending wildcards. The ending wildcard is a better one because the index seek will perform the term for each value, and it will be easier for the B-tree to find all the values. It doesn't need to perform the full scan. So never, or at least be careful. We can see that it's a seek now. Be careful with the like operator. If you have an operator which is like that, you will never have an index seek. It will be slower even though you created an index on the name property. So it doesn't matter whether you have a name index if your query is like this. You may remove the index. It doesn't matter. But if your query is having the wildcard after some term, some search term, you have an index seek, which is, we know that it's better to for the performance. And here is a small example. If we have the wildcard in the middle, the index seek will find O which starts with WI, and then will consider every single one of them. If you have win and then the wildcard, the seek is considerably smaller, and if you have a wildcard at the end, it will be even smaller. And if you have a wildcard at the front of your search term, it needs to scan the whole index, so there's no point of an index. When we talk about multiple columns with indexes, is it better to have two indexes for two columns or a single combined index? I already showed you how to create an index on multiple columns. You just need to add the columns. Remember that ordering is important, so you should consider your queries before creating the order. The answer is very simple in most cases. One combined index is faster because one index scan is faster than two. Duh. And additionally, if you have two indexes, the database will need more CPU power to combine the intermediate results from both index scans. So if you need to add an index on multiple columns, always add a single combined index. It's better for performance. Another thing to consider are filtered indexes. When you have When you have constant values in your data, it may be a good idea to use a filtered index to save disk space and optimize the performance. If you have lots of queries, which looks like this, select something from something, where something equals a constant, for example, a to-do list, in which most of the data entries will be done and some of them will be pending. If you have multiple entries and a lot of queries which search for a constant, and the constant is always the same, you may create a filtered index with a where clause. You may do it with SQL. Directly create index on messages where processed equals n. So you will create an index only on the values which are have the processed column to equal n, and that will make the index smaller. You will save disk space and you will optimize the performance, especially if most of your queries search for that value. So you can optimize the index data by filtering it and not including everything, but including parts of the data which you most frequently use. This will improve the index seek and index scans in your queries, and that's a very huge win. If you don't want to use SQL to create the index filter, you can do it by adding a filter from here. You can say where age is more than 5, for example, or something like that. So you can create a filtered index from the Management Studio too. But filtering indexes is a good way to optimize, especially when the data is mostly used only in parts of it. Other problematic where conditions. First, dates. Usually you use dates with some sort of a function. For example, you truncate, you get only the month of the date but store the full date. We already know that using functions on indexes does not work very well. So how to solve that issue? Just create a pre-computed column and use an index on that column. So if you happen to work with dates and use some functions with these dates, make sure that you index them correctly. Second thing is numeric strings. Numeric strings are a bad practice, but you may find them here and there. And if you save numbers as string, the performance of the index will be very poor. So always use numeric types in your columns and not strings. And last is math. Using math expressions in your queries will not allow you to use the index potential. It's essentially the same as functions. If you try to use math here, for example, age plus 5 is more than 10. A simple operation, but it will perform an index scan on the cat's name property, cat's name index. So essentially the age index we have currently is not useful when we use math. So the answer will be to not use math, because now we have index seek, or if we don't have an option to use, we need to use math in some of our queries. That's completely fine. Then use a function-based index as a solution. Create a pre-computed value, pre-computed column with the computed mathematical expression, and then use an index on that. But again, don't overdo it. Do it only when you find a performance issue. Only when you see that your application is struggling with the queries. That's when you should consider indexing. So what's the typical approach? You create a database without indexes. You don't need them initially. Your application grows, a lot more queries starts to run, the data is becoming huge, and you start to notice that there are problematic issues with the queries here and there. So if you don't want to improve the application layer and if you want to improve the database layer, you get the query, see the execution plan, and see what kind of indexes you may add. You add those indexes, execute the query again, see the execution plan, and if you're using index seek, you've improved the query, so you leave the index there. Otherwise, you may need to improve the application layer by introducing caches. So always add indexes when they're necessary. Don't prematurely add them to be sure in the future, because you don't know for which queries the database engine will be fast and for which queries it will not be. So that's important. Don't add indexes without having any measurements first. So guys, if you have any questions, leave them down below in the comments below this post and I will be very happy to answer them. I hope you like this video. In the next month's exclusive lesson, I'm going to cover more operations, for example, grouping, joining, sorting, and all other considerations you need to have with indexes. I'm also going to cover some additional topics like clustering and, for example, different kinds of myths considering the indexes. So thank you guys again. Thank you for being part of this mentorship program. I really hope you enjoyed these videos. Bye for now.